My apologies, it looks like it's not formatted correctly. So, my name is Diadon, and I'm with the LNR Forum. I'm an experimentalist and researcher, and I'm going to be discussing utilizing machine learning techniques for exploring low-energy nuclear reactions. So, see if I can do this. Doesn't look too bad. I'm gonna try to get through this quick. Yeah, I already heard some laughs, so I better tear through this. So in this presentation, we'll review the phenomenon of low-energy nuclear reactions and explain how machine learning techniques can be used to investigate them. We will discuss the challenges that researchers face in this area and present some initial results of machine learning investigations into low-energy nuclear reactions. Additionally, we will explore the potential applications for machine learning in this field and discuss future directions for research. Why investigate low-energy nuclear reactions? Obviously, energy production, waste management, nuclear medicine, propulsion, space exploration, and fundamental insights to physics. Some challenges in investigating LNR. Lack of theoretical agreement, prediction and control, experimental design, replication challenges, and precision requirements. Precision measurement requirements, that is. How machine learning can help solve some of these challenges. Model development, optimization of experimental design, enhancing replicability, data analysis and interpretation, real-time monitoring and control, collaborative research, automating tedious processes, and enhancing interpreting data, handling interpreting data, let's put it that way. Some machine learning techniques, machine learning is a powerful tool for analyzing low-energy nuclear reactions. It looks at a lot of different data to find patterns, and there's primarily three general types of machine learning. There's supervised learning, reinforcement learning, and unsupervised learning, and then there's semi-supervised learning, which is kind of like a hybrid, and also reinforcement learning with human feedback. Some examples of machine learning techniques. Hopefully you guys can see this all right. In supervised learning, a general example is like email spam filtering and things of that nature. In LNR, it'd be predicting nuclear reactions using support vector machines. Unsupervised learning would be, I'll just use the LNR as example since that's what most of you are interested in. So clustering similar experimental data sets to discover unknown phenomenon and recognizable patterns. Semi-supervised learning is like multimodal models that translate nanoscale topologies into mathematical language and vice versa. And then deep learning, so analyzing gamma ray spectra using convolutional neural networks and things of that nature. And that is a note, just ignore that one. Another useful application is in autonomous research assistants or autonomous agents. You're able to create a recursive agent that can retrieve information from data sets to have factual information rather than, because a lot of times LLMs they can hallucinate, they have the potential to hallucinate. So if they can go and retrieve factual information and you can use that in your lab to interface with other APIs and things like that, then you can create a powerful tool that makes the processes more efficient. So data sets for machine learning. This is a really important part, is data collection. There's some challenges, of course. One is that if people have intellectual property, that can be a bottleneck. You aren't able to collect their data, obviously, so open data sets is important to have. Also, clear and concise data that's formatted properly for machine learning techniques is important. Collecting data through experiments and things like that are an important process. Data pre-processing, so there's data collection, which you gather the raw data from various sources. Data cleaning, you remove noise and handle missing values for accuracy. Data integration, combine different sources into one coherent data set. Data transformation, scale normalized data to encode categories. Data reduction is to reduce the complexity without losing the actual information. And data splitting is to divide into training, validation, and testing sets for model evaluation. Some feature selection is also very important to try to find what it is you're looking for with the machine learning technique. If you are looking for what particles are involved, or you're looking for what anomalies you want to find in your data sets, it's crucial that you choose a path. You decide which task you want the machine to accomplish. Some methodology that I did some preliminary experiments. I did a historical analysis, a statistical analysis, theoretical analysis, looked for experimental commonalities and predictive models and simulations. So this is a historical statistical analysis, and I don't know if something happened in 1989, it looks like, but basically I took data sets from Leonard Canner, so thank you, Jed Rothwell, for allowing open access to that, as well as archive. I used archive and scraped the data from archive. And this is a statistical analysis experiment. This is a Project Proteus experiment I did. This is just a specific heat capacity of water in 600 milliliters of water, and I did a 3D plot to measure the power and temperature over time. However, when I ran the actual experiment, due to electromagnetic interference, it failed. And then gathering theoretical model data collection. There's like 60 plus theoretical models that I could find, and I'm sure there's more. So it's definitely enough to make a researcher's head explode. I also took a theoretical model analysis and did a Venn diagram using my autonomous research assistant or agent. And this is just the 10 most popular models, like Storm's theory and Takahashi's theory, and a lot of them, and the classic D to D fusion. And this is kind of you can see the similarities between the different models. This is a predictive model simulation that looks like it won't play because my formatting was bad, but I will have this all available online so people can go and look at it. And there are definitely some limitations to machine learning, like I said before, intellectual property and legal compliance, accessibility to data, access to the data, hardware cost, computational cost is actually a really big hurdle for myself. You can use cloud computation, or you can buy a really nice fancy GPU, but both are pretty expensive over time, so that is something to consider. And then I also pulled data for collaboration for open science and technology, and just kind of compared open to closed. Now, it's kind of hard to get closed data, so this might be somewhat swayed in one direction, but what I did notice is that when you have open source software, open source science and technology, it tends to spread a lot further in communities, and people are able to share it more for obvious reasons, and it seems to be a little more prolific in society. So, and this is another example of open source versus closed source technology adoption. This is for LLMs in particular. One of the reasons why large language models, which is what LLM stands for, is so popular is because it's very open source. Many of the models are open source, so it allows a lot of people to contribute, to find problems, and to share and iterate. I think it's something that's very important and something we should consider in the LNR field as well. For future directions, one machine learning task that requires further investigation is the underlying mechanisms behind LNR. I think most people can agree upon that. Future research should focus on developing better models that explain the observed phenomenon. Another area needing attention is the reproducibility of experiments. Difficulty in replication leads to skepticism about the results. New techniques for controlling experimental conditions and reducing sources of error will help address these issues. So, in conclusion, utilizing machine learning techniques for investigating low-energy nuclear reactions holds great promise for advancing our understanding of this complex phenomenon. By analyzing large and complex data sets, machine learning can reveal patterns and relationships that would be difficult or impossible to detect through traditional methods. Though supervised, unsupervised, and deep learning techniques, researchers have already made significant progress in identifying key features and predicting reaction outcomes. However, it is important to recognize limitations of machine learning and the need for collaboration with other fields of study. While machine learning can provide valuable insights, it cannot replace the need for theoretical understanding and experimental validation from observations. Moving forward, it will be essential for researchers to work together and share knowledge in an open and collaborative manner to advance the field of low-energy nuclear reactions to help create prosperity and an abundant energy for all of humanity. And here's some contact information. And I'd like to give a thank you to the LNR team and for the University of Chechen for allowing me to come, and everybody who donated. This was all funded through a GoFundMe campaign to get me here, so I really appreciate that. And with that, I'll take questions.
Thank you very much presentation.
Okay, I think it's a very, very useful tool. I think at this time we can have some hope to solve the big problems, but if we look at the reality of cold fusion experiments, usually are made from poor people in some way. They don't have enough instrumentation. And this is, I think, the main problem about self-reproducibility of the experiments, because you don't have done enough tests to check where you make some mistake, the second experiment and so on, or improve.
Right.
So how this machine can help to suggest, see, useful really, I like very much, but the reality of our society is a little bit not wonderful. Okay?
Right. Well, obviously we're humans, so we make errors, and that's something that we all have to address. I think machine learning can help identify certain errors and certain problems, but not completely eliminate the human factor, because it's essentially like an extension of our intelligence. So it can help us identify phenomena that are related. It can help us create simulations that we can then experiment with. But like you said, if the initial experiments are poorly designed or have errors in them, then this machine learning is probably not going to help very much. Right? So.
Little comment. I think the main problem that is we lack of enough analysis of high quality just because budget problem. So how this machine can help to fill the gap, because we don't have, so I am an experimentalist, so I want to see the things.
Right.
So, but if they don't have the machine, how just I can imagine, but not enough.
Well, it can kind of bring together what you would call, I guess, mainstream physics to help identify like the correlations between hot fusion and the cold fusion, and it can help identify creatively gaps in knowledge or or bring, if so long as people are open to share, right, it will bring a lot of people's research together to analyze what is useful and what is promising, so you can go in that direction.
Okay, thank you.
Makes sense.
Just a personal question to you. How many scientific papers personally you have created using the machine learning process?
Collaborated with?
No, personally you.
First of all,
One.
I don't have, one. Yeah, I don't have a whole bunch of scientific papers. This is actually my first. So
It's your first.
this is my first, yes.
Thank you.
Yeah.
Thank you, Diadon. It was, I know how much work you put into presenting this and preparing for it as well, and the thought and the many hours that lay behind it. Francesco raised the subject of quality, the quality of the papers that machine accesses and uses in order to look for correlations. And I think probably there is a fairly simple method of ranking that even a machine could do. It's so simple, which would be to say, well, if this paper doesn't include this kind of analysis, or if it doesn't include, for example, EDX or SCM or something like that in terms of transmutation proof, or alternatively, if it claims excess heat but has no colorimetry data, then that's a fairly straightforward way of actually eliminating the red herrings from your big pile of fish.
Right, correct.
Yeah. Anyway, thank you again.
Thank you.
I think your approach, or generally AI method, is very, very, very nice. It can help us much, I think. But the problem is, of course, data collection. We need a lot of data. If we want to understand something from all the experiments, not only hypotheses are needed, but I think the features or different, very, very detailed understanding of materials that have been used. So you need some chemical, physical, parameters of different materials, and then you can correlate input with the output. So it is a lot of work.
Yes,
it is not so easy, I would say, but it is something. This kind of procedures work in different fields. I hope here can help us as well.
Yeah, I hope so too.
Diadon, well done on your first talk. In support of what Conrad was saying, I imagine a scenario where the community gets better analysis on the spatial arrangement of before and after on different analysis techniques, SIMS and EDS and so forth. Right. And then that gets put into a vision system, learning system, and then we can learn about the spatial arrangements of material coming into and out of the system. So this is not already in the literature. That seems to be one big circle jerk when you put it into AI. And I found someone did an AI on me and said, who's Bob Green? It says he does volunteering for the Martin Fleischmann Memorial Project, and they do replications of Martin Fleischmann's palladium and deuterium experiments, which we have never done. So, but it sounded very authoritative. Right. And to speak to that point, I find that AI is very good from a point of view of the language model side of it, and we can use it practically in applying for grants to bodies to get the language which is compliant with funding bodies. Yeah. It's actually a really good use of the tool which it can actually deliver right now. Yeah. Because it's about having a convincing argument. Right. So, but yeah, I'd like to see it move into analysis which takes so much time of spatial arrangements on products of reactions. Right, and there is a multimodal type of machine learning. It's in the works, which kind of use text, the generative text, but also uses image recognition and the other neural networks processes, and they can intercommunicate with each other. But it's it's in the works, at least in the open source community. It's in the works. Who knows what's happening in private realms? But yeah. So there's also a risk here that with AI technologies on cameras.
Yeah.
particularly, they have an illusion of what is going on. So I'm having to use old Samsung S7 cameras with a microscope attachment because I actually get to see exactly what is on the sample. But if I put it on a modern camera, on a phone camera, I get an imagination of what it thinks is the right thing that the customer wants to see.
Well, it's like a child. You have to train it properly.
Well, no, it's hard-coded into the Samsung S27 or whatever.
To your camera. So there's also like hardware implications. If you're going to need to set if you're doing image recognition or whatever, you need to have a really nice camera or
a really dumb camera.
Or a really dumb camera.
As stupid as possible. Every pixel's a winner. No one's making a guess of what it should be. That's what you want. No AI when you're doing the actual acquisition.
You might have offended many cameras in here, so
I'm sure I have. Good talk, thank you. It's great to have it in the community.
Thank you.
Hello, Diadon. I have a question. Do you know some similar efforts in another industry for like pharmaceutical or farming? How AI could be used? My first intuition is that encoding is really the big problem. But that working with humans in multi-steps, maybe there are organizations, human organizations, for example, people labeling papers because they have SIMs, I've heard that, because they talk of theory, they talk of experiments, they talk of transmutation, first labeling, then you give people to analyze some labels like transmutation, you extract some data and you learn AA to extract data, then you push all your books inside to get more data, then after you get more model, and this means it's something that has been done, I assume,
Yeah,
in some
actually
industry.
I have a ton of data sets. If we go back here, if you go to, you can either email me or if you go to Conscious Energy /LDNR, you can get the data sets there. So it's all, and I also have it on GitHub, and I'm still populating it because I have a crap ton of data sets. So I'm still populating GitHub and Hugging Face, but both those places. If you want the data sets, Hugging Face is a better way to go. But if you want to know the actual code, you would go to GitHub.
Okay, so just one point, I think that we should look what the other industry do and get modest at the beginning because it's very hard domain.
Yeah. Thank you.
Already past time, so I'm closing the session, and I would like to thank the presenters.
Thank you.
Next, we will discuss 20.